So to check that all players always choose trading in equilibrium, we must show that their best responses. So basically we have to show that the buyer would choose to trade when seller follows this strategy, which is to choose say trade for both peach and lemon kind of cars, and vice versa. When buyer says trade, sellers would actually indeed will choose this kind of a strategy. Okay, so to show mutual best response, to show Nash equilibrium. Now let's do the first thing. Let's first test whether buyer would choose trade when seller of both types say trade. Okay, now so basically the question is, so buyer would optimally choose trade as best response to trade by the peach kind and trade by the lemon kind if the expected payoff of the buyer from buying the from engaging in the trade is positive, right? Now notice how to compute in order to compute the expected payoff, we need to have some information about what the buyer thinks about the quality of the car that he's trading, given the strategy chosen by the seller. So before the strategies are chosen, buyer believes that it is of quality peach with Q, probability Q, and with lemon with probability 1 minus Q. Okay, now given that both types of sellers are saying trade, if a trade happens, buyer is still unsure, right? Because both sellers are willing to trade. So buyer doesn't have additional information from the strategy that he can use to update his belief using Bayes rule. Okay, unlike in the previous case. In the previous case, only one type of seller, the lemon type of seller, was willing to trade and the peach type was not. So in case trade happened, the buyer could correctly believe that the car was of lemon type. But given that in this strategy of the seller both types are trading, buyer doesn't get any additional information. So he continues to believe that the car that he will be trading in will be of high quality, will be of peach quality with probability Q, and with lemon with probability 1 minus Q. So there is no additional new updating of beliefs based on the strategy of the seller, because the strategies are identical across all types. Okay, so the expected payoff of the buyer is given by, with probability Q, he gets the peach type, in which case his payoff is 3000 minus P, and with probability 1 minus Q, he gets the lemon type, in which case his payoff is 1000 minus P, and that must be bigger than saying no trade. If you say no trade, you get 0. Okay, excuse me. So this is the expected payoff from trading when seller follows strategy TPTL. Okay, which implies there is no updating of beliefs. Updating of beliefs. Okay, so so this allows us to compute the expected payoff. So this all gives me a range of values. So if I simplify this, I get sorry, 3000 q plus 1 minus q times 1000 minus p is bigger than 0, which implies 1000 plus 2000 q is bigger than p. Okay, so this is the condition that must be satisfied for the buyer to choose trade in response to sellers of both types choosing trade. Okay, now we want to get the opposite thing. So suppose so now seller of lemon type would choose trade as best response. We have to check for each type separately, right? Because each type is choosing an action, optimal action. So the seller of the lemon type would choose trade if his payoff. So if when buyer says trade and he says trade, there will be trade and he'll get P. If he doesn't say trade, he'll get his the value of keeping his car, which is 0, right? So this lemon type will trade as long as P is positive, and which suppose is case. So so the lemon type is never the problematic type. So now let's check the seller of peach type would choose trade as best response if his payoff, which is P, is bigger than saying no trade, in which case he gets to keep his car, which is worth 2000 to him. Okay, so if price is bigger than 2000, then you know for sure that both the lemon type as well as the peach type would be ready to trade, right? Because they get the price, and lemon type will trade as long as P is positive, but the peach type would trade only if P is bigger than 2000, right? Because 2000 is his reservation value. That's what the car is worth to him. So as long as P is below 2000, he is not ready to trade. So we can't have all parties trading in equilibrium if price remains low. Okay, so if price is above 2000, only then the both types will trade. But we have to satisfy this above equation as well for the buyer to say trade as well, right? So both equation 1 and equation 2 must be satisfied for both the seller as well as both the buyer as well as the seller of type lemon and type peach to say trade, in which case there will be efficient outcome. So let's combine these two equations, 1 and 2. What do we get? So combining 1 and 2, what we get? We get 1000 plus 2000 Q must be bigger than P must be bigger than 2000. Okay, now is it possible, is it always possible that this number is bigger than this number? The answer is no. It depends on Q, right? So what ensures that the left hand side is bigger than 2000? Well, if you check, you get that this implies that Q must be bigger than half. Okay, so if Q is bigger than half, only then you can have a price which lies between the two extreme values, in which case there will be efficient trade, right? In all other cases there will not be efficient trades, right? So suppose Q is exactly half. If Q is exactly half, so if Q is exactly half, you get that the left hand side is indeed equals to 2000. Okay, which means that price must be equals to 2000. So when the probability of a car being lemon and peach is exactly equal to half, then the only time there will be efficient trade is if price is exactly equal to 2000, right? In all other prices there will be inefficiency. And if if q is strictly bigger than half, then you can have a like a range of prices for which you can have efficiency. So suppose if q is equals to 3/4, which is bigger than half, then you see that the left hand side is 1000 plus 2000 times 3/4, so it is basically 2500. So price can be any number between 2000 and 2500. Okay, and then there will be efficiency. So basically q greater than half and price in the range 2000 and 1000 plus 2000 q implies let me write the next sentence. Implies we can sustain efficient outcome in equilibrium, i.e. trade by the peach and trade by the lemon would be a Bayes-Nash equilibrium. Only in that case, only when q is bigger than half and p lies in this range. Okay, so in all other cases we will see that there will be inefficiency. Either only lemon will be traded in equilibrium as you have calculated here, right? So as long as p is less than 1000, we'll have only lemons being traded in equilibrium. In all other values for p such that this equation is not satisfied, we'll have case where there will be no trade. Okay, in which case there will be market collapse, and hence that will also be inefficient. Okay, so we see, so basically we find that inefficiency is highly likely to arise in equilibrium of this game. Okay, so we find that as long as that specific condition is not satisfied, in all other cases we'll have inefficiency, either only lemon being traded or no trade at all. Okay, as Bayes-Nash equilibrium of the game. So basically what this phenomenon shows is sort of something similar to what we had studied in the competitive market version of the Lemons model, is that in many cases there will be inefficiency because of this information problem. We are showing the same qualitative result using game theoretic approach, using the concept of Bayes-Nash equilibrium. So this specific case, this specific phenomenon is called adverse selection. Okay, so adverse selection is the phenomenon that in the market there will be more bad quality cars being traded than what is out there in the population of cars. Okay, so in the population of cars, q proportion are peach and 1 minus q proportion are lemon, but we can very likely have equilibria when prices are low, at least where only lemons are traded, only bad quality cars are traded, right? So that will be, so these phenomenon of bad quality items kind of overflowing the market, which may lead to market collapse in, and which will happen in some equilibria here as well. This phenomenon is called adverse selection. So adverse selection is basically the phenomenon of inefficiently high volume of low quality products being traded in the market. Okay, so this phenomenon of high volume low quality product being traded in the market is known as adverse selection. So basically the idea is that bad quality cars sort of flood the market, and good quality cars are not traded because of this information problem, or high risk borrowers only approach for loans, and low risk borrowers do not approach for loans because the interest rate is too high. Okay, so these kind of information problem leading to inequilibrium, bad quality agents in the market or bad quality products in the market being traded in high volume is known as adverse selection. So this is a model of adverse selection. Okay, so the next application that we will talk about within the theme of games of incomplete information is auctions. So what are auctions? Auctions are environment where is a methodology, is a trading mechanism to allocate say one particular good among a potential set of buyers. Okay, so auction is a trading mechanism to allocate one or multiple, we will only study one object auctions, but it's possible to have auctions of multiple objects at the same time. Object among a set of potential buyers. Okay, so this trading mechanism of auction has been around for a long time, and it is an important area of study within game theory. So a lot of people have studied various kinds of auctions and their efficiency properties, equilibrium outcomes, etc. And it's a sort of a thriving area of research. Now we will study a couple of two simple auctions. So now there are various trading mechanisms within auctions. So you can have various kinds of auctions, right? We will talk about two specific ones. So first we'll talk about so let me just list out the two auctions. First, price sealed bid auction, and second, price sealed bid auction. So auction involves a set of buyers who are referred to as bidders, and there is an object to be sold. by the auctioneer. So auctioneer is the seller who has only one object, and say there are multiple buyers. We will consider say 2 buyers. Okay, and the buyers, each of the buyers have some valuation about the object, meaning that they get some payoff if they get the object, and these valuations are different for different buyers. Okay, so each buyer, or in the context of auction we'll refer to them as bidders, each buyer or bidder in auction has a valuation VI for bidder I. Let me write bidder I. Bidder I in auction has valuation VI, and submits a bid BI to the auctioneer, who's the seller. Okay, so each bidder I has a valuation VI, meaning that it is worth VI to the bidder, if he gets the object, so he gets utility VI. Now in order to get the object, each bidder has to bid. It has to post a bid, a price that the bidder is ready to pay to buy the object. Okay, and that bid is denoted by BI, and BI can be any number. It can be equal to VI, it can be less than VI, it can be bigger than VI, whatever. It's a choice, it's a strategy of the bidder how much to bid given the valuation VI. Okay, now the sealed bid part of the auction refers to the procedure where the bids are submitted simultaneously or in a sealed envelope, right? So I submit a bid as a bidder by writing the number that I want to bid in a sealed envelope, and I sort of submit it to the auctioneer in a sealed envelope. What that basically means is that each bidder is announcing the bid simultaneously, because basically what it means is that when I announce my bid, I don't know what others are announcing. Okay, so that makes it simultaneous move game. Okay, so that's the sealed bid part of it. So sorry, sealed bid refers to the process where bidders submit their bids in sealed envelopes, i.e. bidding is simultaneous. Okay, now so that's the seal bid part. An alternative version of the process is an open bid, where when I announce my bid, I don't write it in a paper and submit it in a sealed envelope. I just announce it publicly. So I just shout the number, right? So you probably have seen auctions of those kinds where publicly I say I raise my bid to some higher number, right? So that's an open bid auction. So we are not considering open bid auctions for analysis. We are only restricting our attention to sealed bid auctions, right, where you submit bids without knowing how much others are bidding. Right? It's not publicly done. Now, what is the first price sealed bid auction? In the first price sealed bid auction, the auction process says that the highest bidder will get the object. So first price sealed bid auction, highest bidder wins the object. So only the highest bidder gets his VI, all other bidder gets 0. The second is the payment. The highest bidder pays his bid. Okay, so the highest bidder, so basically auctioneer opens all the envelopes, looks at who has submitted the highest bid, and that person gets the object, wins the object, and that person pays to the auctioneer the bid mentioned in the piece of paper. Okay, so that's the first price single bid auction. Right, this is clear. The second price sealed bid auction, allocation is same as before. So again, the highest bidder wins the object, but the payment is different. Highest bidder pays the second highest bid. Okay, so again, the auctioneer opens all the sealed envelopes, look at who has the highest bid, that person gets the object, but instead of the person paying the bid mentioned by him, he pays the second highest bid. Okay, so the auctioneer looks at what is the second highest bid, and that's the payment made by the highest bidder, right? So the second highest bidder doesn't get anything, nobody gets anything, only the highest bidder gets it, but his payment is that of the second highest bidder. Okay, so that is called a second price sealed bid auction. Okay, so these two are the two prominent forms of auction studied in game theory, the game theoretical analysis of auctions, and we will study what is the equilibrium in this. Now, before we study the equilibrium analysis, etc., the first question to ask is, why is there a process of allowing the bidders to bid, given that there are bidders also have valuations, right? So the whole point of the analysis and the point of complications behind the analysis is that the valuations are unknown, right, to all the other bidders as well as to the auctioneer. This is super important. So the valuations, how much I care about the object. So suppose a painting is getting sold, right, or an antique piece is getting auctioned. How much a specific bidder values it, how much it is worth for that specific bidder to buy that piece of antique or painting is only known to that person, that bidder. It is not known to others as well as to the auctioneer. Okay, so here the important aspect of the context or the model is that valuations VI are only known to the respective bidder. Okay, so each bidder has a type. He can value it highly, he can value it, he can have a low value, he can have a high value, similar to the quality variations that we analyzed in the previous model of lemons. So here again, a bidder can have very high value for a painting or very low value for the painting, and only that bidder knows whether it has a very high value or a low value or a mediocre mid-range value. Okay, and similarly for other bidders, right? So each valuation number is a possible type of a particular bidder. Okay, and therefore his bidding strategy has to be contingent on the type, right? Similar to the case before. So in the market for lemons, the seller's strategy was contingent on the type of the car. For the high car, he could have a strategy of selling or not selling, and similarly for the low quality car. Same here. If the valuation is high, then the bidder may have one strategy for bidding. He may bid a separate number than compared to the case where the bidder's valuation is low. He could have a different bidding number in that case, right? So the bid is a strategy that has to be ideally type contingent, meaning contingent on the actual valuation that the bidder has about the object. And same is true for all the bidders. So all bidders strategies are going to be their type contingent. So bidders I's strategy BI will be a function of VI, and similarly another bidder J, his bid BJ will be a function of VJ. Okay, and that's what creates sort of a complexity in the model. Okay, right? So that's why it is a game of incomplete information, where we can apply Bayes-Nash equilibrium concept, right? So it is still a strategic context, because my likelihood of getting the bid, winning the object, depends on how much others are bidding. So right, so there is interdependency. So that makes it strategic. Moreover, there is incomplete information because valuations are only known to yourself. This fact that only I know my value and nobody else knows, this is called private information. Okay, this is called private information. So we will say that the valuations are private information in this model. So valuations for the object are private information in this model, right? So that's what makes this model a game of incomplete information. Okay, so in the next video we will talk about first how to study the second price auction. So because the analysis of the second price auction is actually easier than that of the first price auction, so we will study the second price auction first, and then we'll move to the first price auction. Okay.